is devoted to paleographs and some generalization of these graphs. And our next speaker is Sergey Goryainov, please.
Thank you very much for the introduction. The title of my talk on Ekr properties of Peisert-type graphs, and this is joint work with Shamila Asgarli, Hui-Chi Lin, and Chi-Hui Ip. Let me give some basic definitions. Let P be an odd prime Q a power of P. Let Fq be the finite field with Q elements. Fq plus be its additive group, and Fq star be its multiplicative group. Given an abelian group G and the connection set S, the Cayley graph KGS is the undirected graph whose vertices are elements of G such that two vertices G and H are adjacent even only if their difference belongs to S. A clique in a graph X is a subset of vertices of X such that any two of them are adjacent. For a graph X, the clique number of X denoted by omega of X is the size of a maximum clique of X. And let me introduce Ekr properties, or EKR properties for short. Given any graph X for which we can describe its canonical cliques, that is typically cliques with large size and simple structure, we can ask whether X has any of the following three related Ekr properties. The first one is just EKR property, which means that the clique number of X equals the size of canonical cliques. EKR module property, which means that the characteristic vector of each maximum clique in X is a Q-linear combination of characteristic vectors of canonical cliques in X. And strict EKR property, which means that each maximum clique in X is a canonical clique. The classical Ekr theorem classified maximum intersecting families of k-element subsets of an n-element subset when n is greater or equal to 2k plus 1. Since then, EKR type results refer to understanding maximum intersecting families in a broader context and more generally classifying extremal configurations in other domains. The book Ekr Theorems, Algebraic Approaches by Gotsil and Miger provides an excellent survey on the modern algebraic approaches to proving EKR type results for permutations, set systems, orthogonal arrays, and so on. The EKR type problems related to a transitive permutation group G can be reformulated in terms of the EKR properties of co-cliques of the dearrangement graph gamma of G, or equivalent with the cliques of the complement. Once we define canonical co-cliques or cliques, we can discuss the EKR properties of G after identifying G with gamma of G. The EKR module property was first formally defined by Miger in 2019. In this context, a permutation group G naturally acts on the vector space W spanned by the characteristic vectors of canonical cliques, which makes W a G module. Each finite two-transitive group has the EKR module property, which was proved by Miger, Spiga, and Tiep. Miger and Sin recently showed that all finite two-transitive groups have the EKR module property. However, the strict EKR property does not hold for permutations for permutation groups in general. Recently, Miger and Razafi Mahatratra have shown that the general linear group GL2Q is such a counterexample. We remark that our results are of similar flavor, although in our context of Peisert-type graph, the corresponding vector space W does not carry a natural module structure. However, we remark that the definition of EKR module property, even for permutation groups, does not need the additional G module structure. In general, the module method, see the paper by Ahmadi and Miger, refers to the strategy of proving that a graph gamma satisfies the strict EKR property in two steps. The first one is to show that gamma satisfies the EKR module property. The second one is to show that EKR module property implies the strict EKR property. As an example of the module method, the paper provides a sufficient condition for the second step above for two transitive permutation groups. And let us discuss the block quiz result in terms of EKR properties. Consider the Peli graph PQ square, which is the Kelly graph defined on the additive group FQ square, with the connection set being the set of squares in FQ square star. Clearly, the subfield FQ forms a clique. Moreover, the set AFQ plus B also form a clique for each A and B from FQ square, where A is a non-zero square. Such square translates of FQ are the canonical cliques in this example. Blockquist proved that these are precisely the maximum cliques in PQ square. So we can reformulate Blockquist result as follows. Let Q be an odd prime power, then the Peli graph PQ square satisfies the strict EKR property. Gotzel and Miger, in their book called Theorem 1, the EKR theorem for Peli graphs. Extensions and generalizations of Theorem 1 can be found in several papers. In particular, a Fourier analytic approach was recently proposed by Chihoy-Ip. You can see the papers on the slide. While we have at least 3 different proofs of Theorem 1, all known proofs rely heavily on advanced tools such as the polynomial method over finite fields. Instead, in this work, we follow a purely combinatorial approach. Although we are not able to give a simple proof of Theorem 1, we prove a weaker version of Theorem 1. We prove that a weaker version of Theorem 1 extends to a larger family of Kelly graphs, namely Peisert-type graphs. And let us define the main object in this talk. Let Q be an odd prime power. Let S be a subset in FQ square star, which is a union of M cosets of FQ star in FQ square star, such that FQ star is a subset of S. That is, S can be written as follows. Then the Kelly graph on the additive group of FQ square generated by S is said to be a Peisert-type graph of type MQ. A clique in X is called a canonical clique if it's the image of the subfield FQ under an affine transformation. As was already mentioned by Chihoy, the following families of Kelly graphs are Peisert-type graphs. Peli graphs of square order, Peisert-type, Peisert graph with order Q square, where Q is congruent to 3 modulo 4. Generalized Peli graphs, GPQ square D, where D divides Q plus 1 and D is greater than 1. And generalized Peisert graphs, GP star Q square D, where D divides Q plus 1 and D is even. Blockquist theorem already implies that Peli graphs of square order possess the EKR module property. In their book, Gotzel and Miger ask for an algebraic proof of this statement, which is problem 16.5.1 in their book, and this problem motivates our work. Our main result answers this problem for a larger family of Kelly graphs. So the theorem reads as follows: Peisert-type graphs satisfy the EKR module property. So this talk is is based on a preprint, on a recent preprint published in January. So you can see this this preprint on the slide. An orthogonal array OAMN is an m times n square array with entries from an n-element set T with the property that the columns of any 2 times n square subarray consist of all n square possible pairs. The block graph of an orthogonal array OAMN denoted by X OAMN is defined to be the graph whose vertices are columns of the orthogonal array where 2 columns are adjacent if there exists a row in which they have the same entry. Let SRI be the set of columns of OAMN that have the entry I in row R. These sets are cliques, and since each element of the n-element set T occurs exactly n times in each row, the size of SRI is n for all I and R. These cliques are called the canonical cliques in the block graph XOAMN. A simple combinatorial argument shows that the block graph of an orthogonal array is strongly regular. And the following sufficient condition for the block graph of an orthogonal array to have strict EKR property was given in the book by Gotsil and Miger. It should be GM 15 here. And we, in our preprint, we gave another proof for this result. Let X be the block graph of an orthogonal array OAMN with the condition n is greater than m-1 square. Then X has the strict EKR property. The only maximum cliques in X are the columns that have entry I in row R for some I and R, satisfying these inequalities. The main ingredient in the proof of theorem 2, so let me recall, theorem 2 states that Peisert-type graphs satisfy the EKR module property. The main ingredient in the proof of this theorem is the following connection between Peisert-type graphs and orthogonal arrays, which is of independent interest. Each Peisert-type graph of type MQ can be realized as the block graph of an orthogonal array OAMQ. Moreover, there is one-to-one correspondence between canonical cliques in the block graph and canonical cliques in a given Peisert-type graph. We then were able to find 2 explicit eigenbases for the positive non-principal eigenvalue of the block graph of an orthogonal array, which led us to the result of theorem 2. Or more generally, it led us to the establishing of EKR module property for the block graphs of orthogonal arrays. We remarked that the idea of viewing certain Kelly graphs geometrically has appeared in the past. See, for example, the master thesis by Nathalie Moulin and a recent preprint by Shamil and Chikhoy for related discussion. However, polygraphs and block graphs of orthogonal arrays are often treated independently. For example, in the book by Gotsil and Royal, also we can mention here the book by Gotsil and Miger, which is already discussed. And in a recent paper by Adam et al., theorem 4, our theorem 4 is the first to make an explicit connection between Peisert-type graphs and orthogonal arrays and allows us to treat them in a uniform manner. It is known that the block graph of an orthogonal array is strongly regular. Thus, theorem 4 also implies the same conclusion for the Peisert-type graphs, we remark that Peisert-type graphs form a subfamily of a well-known family of strong irregular graphs defined on finite fields due to Bravo, Wilson, and Xian. The connection set is a union of semi-primitive cyclotomic classes of FQ square. However, their proof heavily relied on the fact that that we can compute semi-primitive Gauss sums explicitly using Stickelberger's theorem and its variants. See the references. And theorem 4 can be proved using a purely combinatorial argument, thus giving an elementary proof of the corollary below. Corollary 1, which was discussed in our preprint. A Peisert-type graph of type MQ is strongly regular with parameters Q square, with just these parameters, which are quite complicated, and the following eigenvalues. In particular, a Peisert-type graph of type Q plus 1 over 2Q is a pseudo-Paley graph, which was already discussed by Shamil. Another corollary is as follows: if Q is greater than m-1 squared, then all Peisert-type graphs of type MQ satisfy the strict EKR property. In particular, if D is greater than Q plus 1 over square root of Q plus 1 and D divides Q plus 1, then the D Paley graph, GP Q squared D, the generalized Paley graph, has the strict EKR property. It's natural to examine when a Peisert-type graph X enjoys the strict EKR property. While we do not have a general answer to this problem, we exhibit an infinite family of Peisert-type graphs which fail to satisfy the strict EKR property. The following theorem shows that the condition Q is greater than m-1 square in corollary 2 is sharp when Q is a square. Let Q be an odd prime power, which is not a prime, then there exists a Peisert-type graph X of order Q square, such that X fails to have the strict EKR property. In particular, if Q is a square, then there exists a Peisert-type graph X of type square root of Q plus 1Q, which fails to have the strict EKR property. Another aspect of this work is related to Adamar matrices and their generalizations. Recall that Adamar matrix is a square matrix with entries 1 or -1, such that any two columns are mutually orthogonal. Given an indirect graph G, the Laplacian matrix of G is defined by the following condition: L of G is equal to D of G minus A of G, where D of G is the diagonal matrix of vertex degrees of G and A of G is the adjacency matrix of G. A graph G is called Adamar diagonalizable if the Laplacian matrix of G can be diagonalized by an Adamar matrix. It was proved by Berrig, Falat, and Kirkland. Recently, Adam and et al. Studied a larger class of graphs which contains some families of stronger regular graphs. In order to present their result, they introduced a broader class of matrices which include Adamar matrices. A square matrix is called weakly Adamar if it satisfies the following two conditions. The entries of the matrix are from the set -1 -1 0 1, and there is an ordering of the columns of the matrix so that the non-consecutive columns are orthogonal. A graph is weakly Adamar diagonalizable if its Laplacian matrix can be diagonalized with a weakly Adamar matrix. And let us present a sufficient condition for the block graph of an orthogonal array to be weakly Adamar diagonalizable was given by Adam and co-authors. So a large class of block graphs of orthogonal arrays satisfy the definition of weakly Adamar diagonalizable graphs according to the following theorem. Let O be an orthogonal array, OAMN, that can be extended to an orthogonal array with n+1 rows. Then its block graph XO is weakly Adamar diagonalizable. Paley graphs are known to have a close connection with Paley's construction of Adamar matrices. Recently, by Adam et al., it was shown that Paley graphs of square order are weakly Adamar diagonalizable. Our following theorem generalizes their result. It reads as follows: Peisert-type graphs are weakly Adamar diagonalizable. The chromatic number of a graph X denoted by high of X is the smallest number of colors needed to color the vertices of X so that no two adjacent vertices share the same color. We remark that one can prove the original Ekr theorem using a fractional chromatic number of Kneser graphs. See the book by Gottsill and Royal. It is known that the chromatic number is lower bounded by the clique number, that is, omega of X is less or equal to high of X. Breuer, Domen, and Ridley showed that if D is greater than 1 and D divides Q plus 1, then both the chromatic number and the clique number of the generalized Paley graph GPQ squared D is Q. The converse of this result was proved by Schneider and Silva. A stronger converse was proved recently by Chihoib. So these results were already discussed today. Our following theorem computes both the chromatic number and the clique number of all Peisert-type graphs, hence extending the first result on generalized Paley graphs since the first result by Breuer, Domen, and Ridley. Extending the first result on generalized Paley graphs since generalized Paley graphs GPQ squared D with D with the condition D divides Q plus 1. Such a graph is a Peisert-type graph. The theorem reads as follows: let X be a Peisert-type graph of order Q squared, then the clique number of X is equal to the chromatic number of X and is equal to Q. And let us conclude the talk with several open problems. Let X be a Peisert-type graph and W be the vector space generated by the characteristic vectors of the canonical cliques in X. As we mentioned above, there is no obvious choice of a non-trivial group action on W. Finding such a group action already in the case of the Paley graph may give new insights on the Ekr theorems. So the problem reads as follows: does there exist a two-transitive permutation group G that acts linearly on the vector space W generated by the characteristic vectors of canonical cliques in the Paley graph PQ square? Another problem motivated by the counterexamples found in theorem 5 is the following: characterize Peisert-type graphs with the strict Ekr property. And finally, we would like to mention that Peisert-type graphs of order q square can be analogously defined in the case when q is a power of 2. So in our previous consideration, q was an odd prime power, and problem 3 is to investigate EKR properties of Peisert-type graphs in characteristic 2. So we already have some progress on problem 3. Thank you very much for your attention.
Thank you very much for the talk. Any questions to Sergey? Well, okay, at the end of your talk, you mentioned about result concerning chromatic numbers. I'm just wondering, did you study any other chromatic properties of the graph under consideration?
Not yet.
Not yet. Okay, are there any other questions to the speaker? Well, if not, then let us thank Sergey again for his very interesting talk.